video I will tell you guys how you can calculate the refrigerant line size. So in this example particularly we will calculate the liquid line size. Also we will calculate subcooling required at TX wall for proper operation. So let's start. As you can see in the figure, we have a condenser over here and the evaporator over here that is higher than condenser with a riser of 20 feet. And you can see that this green color is the liquid line, and the liquid line is consist of following components over here. You can see that is 22 feet of piping, 7 long radius elbows, 1 filter dryer, 1 side glass, and 1 globe type isolating valve. How we have 7 long radius elbows? As you can see, this is the 1 elbow, this is 2, this is 3, this is 4, this is 5, this is 6, and this is 7. So we have 7 long radius elbows over here. So let's move back to our Excel sheet over here. So this is our design parameters. Evaporator operated at 40 degree Fahrenheit, condenser operated at 120. Material we are going to use is copper. Refrigerant of 10A we are going to use, and the system capacity is 60 tons. And the system capacity we have calculated, we have already calculated using that software, so we know that system capacity is 60 tons. So over here, refrigerant of 10A, we have write the components and the number of components used over here. Then before giving this equivalent length for each component, let's move forward and first calculate the estimate pipe size over here for 60 ton capacity. So let's move over here. There we have a refrigerant line size table or 410A refrigerant. So as you can see that this is for suction line, this is for discharge line, and this is for liquid line. And you see over here we have a pipe dia in inches, and over here inside this is the system capacity. So we have to follow this liquid line, and our system capacity is 60 ton. We know it will be in between 45.8 and 79.7. As you can see over here, I have highlighted here. So we will not go for 45.8, we will go for 79.7, higher side, safer side. So for 79.7, as you can see, 1 3/8 is the pipe size. So we can use this 1 3/8 inch pipe size. So let's move back over there and see 1 3/8 inch is the pipe size we are using over here. And actual system capacity, you know that it's 60 tons. And the table capacity is the same. We know that it's 79.7 ton. This is the table capacity we have used over here for 1 3/8 inch. So we have to write this table capacity 79.7. So we have write 79.7, and this table is for 100 feet length. So we have to write this table length also 100 feet over here. Now we'll move to equivalent length now. As you can see over here, down there I told you this 22 feet piping, straight piping length. So we have write 22 feet over here. So long radius elbows we have 7. So what is the equivalent length for each long radius elbow? Let's move back over here. And there you can see equivalent length for the fittings. Smooth elbows 90 degree elbows for 1 3/8 inch. This is the equivalent length 2.3 for 1 3/8 inch. So this one we are going to use 2.3. As you can see 2.3. So for filter dryer, side glass, and solenoid valve we have to check. This is the equivalent length for the valves and other devices. As you can see, 1 3/8 inch, 38 feet is for globe or solenoid valve, So this is the 38 for global solenoid valve. Now go for side glass. For side glass, for filter dryer core it is 35 and side glass it is 2.5 for 13 by 8 inches. So 2.5 for the side glass and 35 for the filter dryer core. As you can see, 35 for filter dryer core and 2.5 for side glass. So if you multiply this number of items with this equivalent length, you will get fitting equivalent length for each and every component. So simply multiply this with this, you will get to the fitting equivalent length. And if you will sum all of these components equivalent length, you will get total equivalent length in this column. That is 113.6. So up till here it's done. Now table length is done. Now table delta T. What is the table delta T? It's 1 degree Fahrenheit. How it comes, I'll tell you. Let's move back over here. As you can see, for the liquid line we have used this 1 degree Fahrenheit delta T. So we have to write for table delta T, that is 1 degree Fahrenheit. These are the system capacities. So this one we have used over here, 1 degree Fahrenheit. So this one we have to write 1 degree Fahrenheit. Now actual delta T, this is calculated by using a formula. I will show you what's the formula I have used over here to calculate actual delta T. This is the formula I have used over here for calculating the actual delta T. We know the actual capacity, table capacity, we know actual length, we know table length, we know table delta T. So all of these components we know. So by putting the values we can calculate delta T actual. So this is a formula I have applied over here to calculate delta T, actual delta T. Now we have to calculate the pressure drop from the table. So this is 4.75. How it came, I will tell you. As you can see over here, for 1 degree Fahrenheit, what is delta P? As you can see that pressure drop. This is the pressure drop. This 4.75. So 1 degree Fahrenheit, what is the pressure drop for R410A refrigerant? That is 4.75 psi. So this one we have to use for the table. Delta P 4.7 psi. This is the 4.75 psi. Now actual piping pressure drop we have to calculate. This also calculate by using a formula. I'll show you the formula. This is the formula we have used over here for pressure drop actual calculation. So pressure drop for the table, delta T actual divided by delta T table. Actual delta T we have already calculated from this formula. Delta T table we know that it's 1 degree Fahrenheit, and pressure drop from the table we already checked from the table, that is 4.75 psi. So putting all these values you will get actual delta P. So this is how you can calculate actual delta P. As we know that riser height, we'll move back to our diagram over here. Riser is also used over here. So what is the riser height used over here? That is 20 feet riser. So we have 20 feet riser height, refrigerant pressure drop per feet. Again we have to use a table for this one. What is the refrigerant pressure drop per feet? Since we are using R410A refrigerant, so we have to check what is the pressure drop for this refrigerant per feet. So move back over here, go down. There's a one more table, this one, pressure drop in liquid line by refrigerant. As you can see, we're using R410A refrigerant, and this is the pressure drop, that is 0.43 psi per foot for R410A refrigerant. So we have to write this one, 0.43 psi. So we have write this 0.43 psi per foot. So if we multiply this refrigerant pressure drop per feet multiply with this riser height, will get the pressure drop from the riser. So multiply these two, will get pressure drop from the riser, 8.6 psi. So multiply 0.43 with 20, will get 8. So let's move forward. we have calculated this pressure drop from the riser. Now we have to calculate what will be the total pressure drop in the liquid line. So in order to calculate this total pressure drop, you have to sum from the riser and actual pressure drop. So you have to add these together, actual piping pressure drop plus pressure drop from the riser. These two add together, you will get total piping pressure drop. So 3.23 plus 8.6, you will get 11.4 psi, 11.84 psi. So move forward. Saturated pressure at 120 degree Fahrenheit. We know that condenser operate at 120 degree Fahrenheit. So this is the saturated pressure at condenser. So we want to calculate now saturated pressure. What will be the saturated pressure at 120 degree Fahrenheit? We can calculate this by using PT chart. So let's move back over there. Here we have a PT chart. We will go for R410A refrigerant. So this is R410A refrigerant, as you can see. So this is the temperature in Fahrenheit. So we are going to use 120 degree Fahrenheit. What is the pressure for R410A refrigerant? As you can see, this is the pressure, 418 psi is the pressure at 120 degrees Fahrenheit. So this is we have to use over here, 418 psi. So we have used 418 psi over here. Now saturated pressure of refrigerant at TX valve. How we will calculate this one? We have to subtract 418 minus, we have to subtract this 418 minus total pressure. You will get saturated pressure of refrigerant at TX valve. So saturated pressure at 120 degree Fahrenheit minus total pressure, you will get saturated pressure of refrigerant at TX valve. So move forward over there. Now saturation temperature at TX valve. How you will calculate this one? Now we know what is the saturated pressure of refrigerant at TX valve, that is 406. So from the PT chart we can calculate the saturation temperature at TX valve. So move back. What is the pressure? 406. 406. As we can see that we have 391 and 418. So we have to perform iteration in between 115 degree Fahrenheit, 120 degree Fahrenheit, 391 psi and 418 psi. I hope you guys know how to perform the iteration. It's quite easy. If you don't know, then let me know. I will tell you how you can perform the iteration to calculate this delta P, that is pressure drop. So this is how you can calculate. Move back. Okay. So after performing the iteration, you will get 117.8 degree Fahrenheit saturation temperature at thermostatic expansion valve by performing the iteration. If you don't know about the iteration, let me know. I will tell you how you can do it. So let's move back over there. Actual saturation temperature for the condenser is 120 degree Fahrenheit, we know. So this is now we are the final step of calculating the subcooling. Now the subcooling for saturated liquid at thermostatic expansion valve is 2.2. How it comes up? So we have to actual saturation temperature minus saturation temperature at TX valve. You will get subcooling for the liquid at TX valve. So as you notice, this 2.2 degree Fahrenheit is the amount of the subcooling required to have saturated liquid refrigerant at TX valve. If it is less than 2.2, refrigerant will start to flash and TX valve will not operate properly. For TX valve to operate properly and to avoid diaphragm flutterings, there should be an additional 4 degree Fahrenheit of subcooling. So the minimum system requirement we have to add over here. we have to add additional 4 degree Fahrenheit for thermostatic expansion valve to work properly. So the minimum system requirement is 4 degree Fahrenheit. So what is the actual subcooling for the proper operation of TX valve? It will be minimum system requirement plus this subcooling for saturated liquid at TX valve. So this is 6.2 degree Fahrenheit is the subcooling required for proper operation of thermostatic expansion valve, so that refrigerant will not flash. So this is how you can calculate this liquid line size and subcooling. Guys, about equipment selection as per your calculated heat load. So this is the sheet I am going to use over here. If you have seen my previous tutorial number 16 and 17, in which I have already explained how to calculate the heat load using E20 form and HAP software, so I will continue by following the same procedure from there. So let's move. So first you have seen there I have 4 different rooms over here. I'm going to select the AC machine as per this calculated heat load. So there I have a catalog by Jock. So I'm going to select a machine from this sheet. So first we have a recreation room, and in the recreation room, as you can see that we have already calculated the heat load, and TMBH over here is 18.13 and T kilowatt is 5.26, TSMBH is 16.9 and TS kilowatt is 4.9. so and CFM is 826 and 388.5 liter per second is the airflow rate. So all of the values I have already put here. The first one is in TMBH and the second one 5.26 is in the T kilowatt. Same in this column, same in this column, that is CFM. First one is the CFM 827 and second one is 389 liters per second, that is the airflow rate. So I have already put all the values over here. So I'm gonna show you how to select the machine. So let's move to this catalog. First focus on this CFM airflow rate, that is CFM or liter per second. I'm going to select the machine as per 389 liters per second. So if I move to this chart 389, okay, if we go to this airflow column in liters per second, 389, it's exactly not there, so we will select the nearest one, that is 442 is the nearest one. Or we can do one more thing, we can select 2 FCUs. This is FCU2 198 liter per second and FCU3 198 liters per second. So 198 2 FCUs, if we will select, it will be 396 liters per second. And how much is over there? 389. So it's okay, we can select this one with 396 liters per second. So we are going to select 2 FCUs for recreation room, that is 198 liter per second and 198 liters per second. So it will be 396 liters per second. In this column I will put only in liters per second. Okay, so how much is the TS kilowatt or T kilowatt, we will also see over there. This column is for kilowatt, there is total duty kilowatt and other is sensible duty kilowatt. So it will be 3.88 because we are selecting 2, so it is 7.76. total duty kilowatt 7.76. And TS kilowatt, how much? That is sensible duty. It is 2.68, 2 times, because we are selecting 2 FCUs over here. It is 5.36 sensible kilowatt, 5.36. So this is how you can select the machine. So 389 liter per second is our calculated, and obviously we have to go for the higher, we will not go for lower. That's why we have selected 396 liters per second. Okay, in the same way we are going to select the machine for showroom 1, showroom 2 and multi-sitting area. So what we have over here is 1406 liters per second is the airflow rate. So let's move to the catalog again. 1406 liters per second. As you can see that maximum over here is 938 liters per second. Okay, we will select 938 liters per second. 1406 is the total. So we are left with 468 liters per second. 468. So 468 is not there, 442 is there, and higher number after 442 is 518. So we are going to select 2 machines for showroom 1, that is 938 liters per second and 518 liters per second. That is 938 plus 518. So total 1456 liters per second. Okay, so what is the TMBH and TS kilowatt? Same we can check over there. For 938 T kilowatt is 15 point, that is total duty kilowatt is 15.36, and 518 liters per second machine it's 9.85. So total 25.2 total duty kilowatt, 25.21. And then TS kilowatt, that is sensible duty kilowatt, how much? For 938 liter per second, that is FCU2, and that is FCU5. So FCU2 it's 11.48, and FCU5, that is 518 liter per second, is 6.91. So 18.40. 18.40. And so you can see that calculated heat load is that much, and the airflow rate for that machine is 1406, that is calculated, and from the catalog we have selected 1456, that is 1456 liters per second. As I told you, we will select machine on the higher side, we will not go for the lower side for safety. In the same way we will select showroom 2. As you see that 1624 liters per second, that is the calculated airflow rate. So let's move to the catalog again. 1624. As I told you, 938 liters per second is the maximum available there. So we will select 2 or 3 machines. So 938, 1624. So one machine if we select for 938 liters per second, so we are left with 686 liters per second. So 686 liters per second. 628 is there. Okay, if we will select 2 more machines of 371 liters per second, how much it will be? 686. will be 742 minus 686. So okay, so we are on the higher side, so let's select this machine. 2 FCU number 1 quantity 2, that is 371 liters per second, plus one machine FCU 2, that is 938 liters per second, so 1680 liters per second. So 3 machines we have selected for this area. 1680 liters per second. And same way we'll go and check TMBH and TSMBH, or T kilowatt or TS kilowatt. So as we have seen that 938, that is FCU2, total duty is 15.36 plus, and we have selected FCU1 2 quantities, that is 371 liters per second, and its total duty is 6.53. 2 times we have selected 2 machines, so total 28.4 total duty kilowatt, 28.42. And then we have to check TS kilowatt. So FCU2 938 liter per second, sensible duty is 11.48, and FCU number 1 we have select 2 quantity, that is 371 liter per second, and sensible duty is 4.82. So total sensible duty is 21.1. So as you have seen that the calculated airflow rate is 1624 liter per second, and we have selected 1680 liters per second. So we have to use 3 FCUs over here to fulfill this requirement of 1624 liters per second. So this is how you can select your machines as per your calculation. In this video I will tell you guys how you can calculate this diffuser size, and you can select diffuser from the supply data sheets. So let's start. Let's take an example of this FCU 3FC L1. As you can see that we have got 3 diffusers over here, 3 supply and 3 return, 3 supply and then 3 return, 2, and this is a third return. So I will tell you how you have got 9 by 9 inches for that diffuser. As you can see, the machine CFM is about 199 multiplied by 3, it's 597 CFM. So if you want to check the size of the diffuser for 199 CFM, because machine CFM is 597 and 597 divided by 3, we got 199. So we have got 3 supply return diffusers, 9 by 9 inches, 199 CFM each. So this is the formula we are going to use to calculate this diffuser or air terminal size. What the CFM we got over here is 199. So CFM divided by 400 multiplied by 144, and if you will take the square root of this one, you will get the diffuser size in inches. So how much we got over here is 8.46 inches. And if you know the standard size for the industry, it's 6 inches, 9 inches, 12 inches, and 15 by 15 inches, 18 by 18 inches, like this. So the diffuser which we can use over here is in between 6 inches and 9 inches. If you will go for 6 inches, it will be undersized. So we'll go for the higher side, so 8.5 inches. So we'll go for 9 inches. So this is how this diffuser size is coming. So 8.46 inches we are going to use, 9 inches, 9 by 9 inches supply return diffuser we are going to use over here. So let's move to another FCU to do the same exercise once again. As you can see that here we use 5 diffusers, 179 CFM each, 9 by 9 inches. So let's check this one also. CFM divided by 400 multiplied by 144 and take a square root of this one. We got 8.02 inches. As I told you, standard size is 6 inches by 6 inches, 9 inches by 9 inches. So we'll go for 9 inches by 9 inches for this one. So as you can see that we have used 9 inches by 9 inches over here. So let's move to the supply data sheet, how you can select diffuser from the supply data sheet. As you know, the different type of diffusers we can use: ceiling diffusers, one way, two way, three way, or perforated ceiling diffusers like this, and different decorative type ceiling diffusers we can use. As you can see that this supply air ceiling diffuser 4-way is here, and this is the size in mm. 9 inches equivalent to about 225 by 225. So we'll go over here and let me zoom this one, and as you can see that this is the velocity in meters per second, this is the flow rate in meters per second, this is the velocity in meter per second, this is the pressure drop in a pascals, and this NC is the noise criteria in decibels. So we will have to go for 225 by 225, and we know the flow rate for this one. If we want to convert this, as you know in the drawing, how much it says 199 CFM. So let's convert 199 CFM to liters per second. It will be 94 liters per second around. So if we'll go over there for 225, the 94 liters per second, it will be in between 92 and 104. So this is how you can select diffuser from supply data sheet. And noise criteria will be, if you will go for it will be less than 15 decibels. So between 92 and 104 it will come somewhere here. So you can also get the noise criteria in decibels, and you can also get the pressure drop in a pascals in between 9 and 11. It will be like 10 pascals. So it will also be helpful for you to calculate the fan ESP later on. So this is how you can do the diffuser sizing, and you can select diffusers from supply. Today I am going to explain you guys the duct traverse topic, like how to perform the duct traverse to get the accurate velocity reading, and then calculate the actual volume flow rate across the duct to compare it with the design airflow rate. And this we are doing for air balancing purpose. So let's start. As you can see that we have this duct, and if we want to perform a traverse on this duct, we need to make holes to get the flow rate, and the instrument which we are going to use to perform this traverse is the velocity probe or pitted tube. When you are using the pitted tube, it will give you the velocity pressure. Then the individual velocity pressure must be calculated for each velocity pressure reading, and then averaged together to measure the velocity pressure, and then converted into velocity in feet per minute. So as you can see that this is the duct which we have, and we have inserted the pitted tube inside to get the velocity pressure. As you can see that pitted tube basically measures the total pressure and the static pressure to determine the velocity pressure. So you can see that this is the manometer, and the positive port of the manometer is connected to the total pressure port. This is our total pressure, and this one is connected to the positive pressure port of this manometer, and the negative is connected to the static pressure. And when you insert the pitted tube inside, it basically senses the total and static pressure, and the manometer over here and it measures the velocity pressure. That is the difference between total and static pressure. When you insert the pitot tube inside the duct, make sure that this tip must be pointed directly in, and it should be parallel to the airflow rate. This is the airflow rate and this is the pitot tube. Make sure that it is parallel with the airflow rate. If you put the pitot tube accurately, then velocity pressure indications will be at its maximum. So when you are using pitot tube inside the duct, you will get the velocity pressure reading on this manometer. Then you need to convert this velocity pressure reading into the velocity, and then using Q is equal to VA formula you can get the actual flow rate. And so this is the table which we are going to use for duct traverse of rectangular ducts. As you can see that this is the whole quantity required, and this is the interval C, interval B, and this A is representing as the duct dimension. That is 10 inches, 12 inches, 14 inches. And this table, the duct size is applicable if duct size is less than 48 inches. And for this table we need to refer to figure 1. This is the figure 1, and the interval which I have explained above, that is B and C, you can check from here in this figure. This is the dimension of the duct represented as A, as you can see over here. If we have 10 inches duct size, then A will be 10 inches. Then we need to check how much is the interval B and interval C, and how many holes required for duct traverse. 4 holes required, and B is 1.25 and C is 2.5. So the B is a distance from the inner wall of the duct to the center of the first hole, that is 1.25 for 10 inches duct, and then C is from center of first hole to the center of second hole, that is 2.5 for 10 inch duct size, and the whole quantity is 4, we already know. So we have 4 holes, 1, 2, 3, 4. So it depends on your duct dimension. If you have 30 inch duct size over there, then you need to make 5 holes with the interval B and C as B as 3 inches and C as 6 inches. And this table is applicable if duct size is less than 48 inches. If you have a duct size more than 48 inches, you still need to make 8 holes to perform the duct traverse. But the interval B and C, if you need to calculate the intervals, that is hole to hole distances, and from the inner wall to the first hole, and then from inner wall to the last hole distance, you need to get these distances from this figure. So as I already explained you, we can use either velocity probe or the pitot tube to perform this duct traverse. If you perform duct traverse with the velocity probe, you can get directly the velocity, but if you perform this with the pitot tube, you will get the velocity pressure, and then you need to convert this velocity pressure into the velocity by using this formula. That is, velocity is equal to 1096.7 into square root of HV divided by D, where V is the velocity in the feet per minute and HV is the velocity pressure in inches of water from the measuring device, and the measuring device which we use in the pitot tube, that is manometer, and D is the density of the air in pounds per cubic feet. If we are using this velocity probe, we can get directly the velocity readings like over here. So let's take an example. We have 48 inches by 40 inch rectangular duct, and we need to perform a duct traverse on this duct to get the actual flow rate and compare it with the design flow rate. So if you go for 48 inch duct size by 40 inch duct size, so let's take one dimension of this duct is 48 inches and move back to our table over here. So as per X-ray and slackness standards, for 48 inches duct size, Hole quantity is required is 8, and the interval B and C is required as 3 and 6 inches. So number of holes required are 8. And for the second dimension, that is 40 inches, over here, number of holes required are 7, and interval B is required as 2.85 and interval C is 5.71 inches. You can refer to this figure to calculate the intervals, that is B and C, for 40 inches and 48 inches duct dimension. So since the number of holes required for 48-inch duct dimension is 8 and 40-inch duct dimension is 7, so we need to make a matrix of 8 by 7, that is 56 number of points. We need to make a matrix of 56 points. As you can see that this is the position from A to H. We have total 8 points, that is representing as 48-inch duct dimension, and it is from 1 to 7, that is representing the duct dimension of 40 inches. So this is how we have created 56 number of points, that is 8 by 7 matrix. If you have 42 inches by 30 inch duct size, then you need to make a matrix of 7 by 5. So since we have 48 inches, the example which we are considering right now is 48 inches by 40 inches. That's why we have created 56 number of points, or 8 by 7 matrix. So after creating the holes, we need to insert that pitted tube inside to get the velocity pressure reading at the manometer. Let's say this is 48-inch dimension and the other is 40-inch duct dimension, and we have 8 holes over here and the 7 holes on the other side. So we need to insert the pitted tube at the first point here, that is called point A, and the other one is point 1. So if we put the pitted tube inside at point A1, we will get the velocity pressure reading at point A1, and then from A1 to next A2, then A3, then A4, then A5, then A6, and then A7. If we move to this point, this will be B point at 48-inch duct dimension. So we need to put that pitted tube inside at point B1. This is called B1. If you move inside more, it will be B2, then B3, then B4, and so on and so forth. We need to put the pitted tube one by one, and we need to get the velocity pressure readings at different points. So this is our matrix, and we need to put the reading whatever we got from pitted tube, but make sure that the reading which we got from pitted tube, it's in from the reading which we got from manometer, it will be in the velocity pressure. It will be the velocity pressure. So we need to convert this velocity pressure into the velocity by using this formula. So after using this formula, we will get the velocity in FPM. So let's say we got the velocity at point A1 is 885. This is just an example. You need to go to the site and you need to use this pitted tube to get the velocity pressure, and then you need to convert the velocity pressure into the velocity, and then you need to put that reading over here at point A1. So let's say at point B5 we got this reading over here, and then you need to write each and every reading over here, and after writing all the readings, you need to sum at the point 1 and point 2, 3, 4, 5, 6, 7. So this is the duct traverse for 48 inches by 14-inch duct. So the number of points which we have taken for the reading are total 56. That is 8 by 7, and total number of points are 56. So we need to write number of points, reading points, that is 56. And now we need to calculate the average velocity. So we need to write the average velocity over here. So first we need to sum up all of these velocities. So the velocity which we have over here is 7244, and other point is 7442.9 and 7464, then 7263 and 6889.75, and then 6594.48, then 6437. So total velocity is this much, but we need to calculate the average velocity. Since we have taken 56 points reading, so we need to divide this with 56. So 881 feet per minute is the average velocity. So this is the average velocity across 48 inches by 40 inch duct. So let's say in the drawing we have a design airflow rate is 11,700 CFM. Now we need to calculate the actual flow rate across this duct by using this duct traverse method. So by using this equation, Q is equal to VA. Here Q is the actual flow rate that we need to calculate, and V average is the velocity which we have already calculated over here, that is 881 feet per minute, and A is the area of the duct, and V average, it is in feet per minute. We already calculated above, that is 881 feet per minute, and A is the area of the duct. So as we know that it is 48 inches by 40 inch duct. I will convert this into feet. 48 inches in the feet, it will be 4 inches, and the other one will be 3.33 feet. So 4 feet by 3.33 feet. So how much area we will have? That is 3.33 multiplied by 4. You will get 13.33 square feet area. So now we know the average velocity across 48 by 40 inch duct, that is 881 feet per minute, and the area which we already calculated here, that is 13.33 square feet. So we need to put the values in this equation, the average into area, that is 881 cross 13.33 square feet. So we'll get the actual CFM, 13.33 multiplied 881, so we got 11,746 CFM. 11,746 CFM. So the actual CFM which we got across this duct, 48 inches by 40 inch duct, is 11,746 CFM, and the design flow rate which was in the drawing is 11,700 CFM. This is just an example to show you how to perform the duct traverse. So this is how you can perform a duct traverse to get the velocity pressure from the pitted tube, and then convert this velocity pressure into the velocity, and you need to get the area of this duct, and using this average velocity in this equation you can calculate the actual flow rate across that duct and then compare it with the design flow rate. So this is how you can perform. In this video I will tell you guys how you can calculate GPM for fan coil unit or air handling unit. So let's start. They have open drawing. As you can see that there I have a schedule for fan coil units. This is a schedule provided by carrier company. So as you can see that this is the unit description, this is the area served by the unit, the type of the unit, quantity, model, total capacity in NBH, airflow in CFM, water flow in GPM, ESP, that is external static pressure, motor power, and unit dimensions. So this is a summary or performance sheet for every block I have over here. This is for third floor and the fourth floor I'm showing you. So let me show you how we got this 2.43 GPM for this FCU. So before showing that, I want to tell you something over here. If you can see, in a case of district cooling, you can see that we are normally maintaining delta T of 16 degrees, and by using this formula 1 TR is equal to 24 GPM divided by delta T, we got 1 TR is equal to 1.5 GPM in a case of district cooling. And in a case of chillers, we are normally maintaining 9 to 10 degrees. So in a case of chiller, we got how much 1 TR equal to 2.4 GPM. So let's move back to our drawing. Just keep this in our case, we are using water from district cooling, so we are going to use this formula 1 TR is equal to 1.5 GPM. Okay, as you can see that how much is the MBH over here for this machine, that is 19.47. So 19.47, if you divide this by 12, you will get the tonnage. So how much tonnage you got over here is 1.6225. As I told you, 1 TR is equal to 1.5 GPM in a case of district cooling. So this is the tonnage we got. Multiply this by 1.5, you will get GPM. So how much GPM we got? 2.43. As you can see that 2.43 is the GPM over here. So let's move to another FCU. This is another FCU with getting MBH of 49.32 MBH. So 49.32 MBH, 49.32 divided by 12, you got the tonnage. Multiply by 1.5, you will get the GPM. So how much GPM we got here? 6.165, that is 6.17. As you can see, 6.17 GPM over here. So in the same way you can do for air handling units and all of the FCUs over here in the same way. So this is how you can calculate a GPM for fan coil unit or air handling unit. I hope you guys learned something from this video. Please like, comment, share, and don't forget to subscribe my channel. Thanks.